Let us start this lecture with a thought process from Albert Einstein, who says, look deep into nature and then you will understand everything better. But unfortunately, we do not have time to look deep into nature, and nor we understand anything in life or in otherwise. So, in the last lecture, we basically looked at a very simplified analysis based on the phenomenology. What is happening, then trying to relate those things. And we have seen that we can derive a relationship for laminar flame height or flame length. Sometimes people call it flame length also for a jet diffusion flame, and we have extended that analysis for turbulent jet diffusion flame, and we have seen it is roughly matching at least the trend of the experimental data. And now we will be looking at laminar flames, and we look at theoretical analysis of this, and we are considering here a two-dimensional jet diffusion flame. Here, that is two slots are there, right? These are the two slots, and these are two passages which two-dimensional, having L1 is the length, and this L2 minus L1, this portion, right, which is in which oxidizer is passing through. Keep in mind that this is the x direction and y direction and z direction in this way, right. And this flame is basically two-dimensional in nature. Okay. You can call it as a slot burner, because it is like a slot, right. And generally people do not use that much, except maybe this thing. People always very happy with the tube burner or the jet kind of thing burners, where you use a circular pipe or some other pipe and then use it. And we will be using this analysis for this two-dimensional diffusion flame, because this is basically 2D diffusion flame, right. This is a diffusion flame and 2D in nature. That means what? It is basically changing with respect to x and y, and the z direction is not changing at all, right. That is why it is 2D, and people will be always be happy with the axis symmetric burner also, right. Let us consider is a simple one, and we will make some assumption, and some of the assumption will be repeated, or whatever we have done for phenomenology will be valid here. That is, first is this is a two-dimensional steady laminar inviscid flow. That means it is not viscous if it is not there, and it is steady. And velocity above the channel, right, these are the channels, right, these are all channel, the channel through which fuel is passing, and this is another channel, right. Right. Where the velocity above the channel, that means here it will be remaining constant, right, kind of things. You can say that, right, and it will not be changing. And we will be using basically thin flame approximation I have already discussed, in which fuel oxidizer react in stoichiometric proportion at the flame surface with infinite reaction rate. That means reaction rate will be very fast, right. And that means, what is the meaning of this? That means on this flame surface, right, if it is oxidizer is passing through it, will not cross this flame surface, right. It will not enter into, that means no oxygen will be found in this region, where, right, in this region no fuel will be found, no fuel will be passing through the flame surface and reaching the oxidizer stream or oxidizer side, right. That is the thing. That means at the flame surface, in this flame surface, what will be? YF will be 0 and what else? Y oxidizer also will be 0 at flame surface. Keep in mind, this is your flame surface, right? And that we call it as a thin flame approximation. And binary diffusion between participating species, right? We are saying only fuel and oxidizer is there, two species which will be playing important role, but in real situation it won't be. Why? Because the chemical reaction will be taking place. When chemical reaction taking place, there will be several number of species will be participating, right? And that too, if it is a jet diffusion flame, soot will be coming, there will be patch, and there will be some other things which will be quite complex, right. So, however, we will be doing for simplicity, and mass diffusion is along the x direction. That means the mass has to diffuse in this direction only, in the x direction. There won't be any mass diffusion in the y direction. However, both the diffusion should be there, we had seen, but here the mass diffusion along the y direction is predominant as compared to the mass diffusion along the y, because along the y what will be predominant? The momentum will be predominant, okay, along the y direction, vertical direction, right. So, therefore, as compared to the mass diffusion along the x, the y direction mass diffusion is negligibly small. That is the meaning of this. And unity Lewis number means basically alpha, that is thermal diffusivity, is equal to mass diffusivity, right. And that means that is the things what it will be unity Lewis number for Le is equal to 1. And single step chemistry which will be there, single step chemistry means is a 1 mole of fuel is reacting with new moles of oxidizer going to the product of nu 1 per nu plus 1 kg of the product. And radiative heat transfer is negligibly small, but flame surface always will be radiation will be, but we are not considering, like in the premix place also we did not consider that. And constant thermophysical properties, as usual we have taken this assumption, and mass diffusivity for both fuel and oxidizer are same. That means dF of oxidizer between is equal to d oxidizer fuel, basically that, between this binary both are same, need not to be same, but we are considering it to be same. And buoyancy effect is neglected, that means there is no effect of buoyancy in this case what we are considering. So, with this these things we will have to now look at the various mass conservation equations. Keep in mind that what we are saying, that velocity above the channel is basically remaining constant everywhere. That means the Vx, if you look at, is basically along with the x direction, what will be the Vx? Will be 0, only the dominant velocity is Vy. That is the thing what we will be considering. So, let us look at conservation equation, mass conservation. For the steady flow, we know that this is dou rho Vx divided by dou x plus dou rho Vy divided by dou y is equal to 0. And in this case, there is a Vx is not changing in this flame region. So, therefore, this term will be 0 as Vx is 0, that we are considering. Means what is saying is basically, that is with assumption 2 what you have done, that is with this what we are saying is that rho Vx is equal to 0, if we integrate is rho Vy is constant, right. That means Vy and this density which will be remaining constant throughout this flame domain, right, in the along the this region. That is the meaning of this. and we will look at y momentum, because x momentum already is 0. So, we are not considering. So, axial momentum what we are considering along the y direction is rho v x dou rho v x v y divided by dou x plus dou v y divided by dou y is equal to dou by dou x mu dou v y by dou x, and rho infinity minus rho is into g, right. And this is basically done because of fact that you might be knowing this rho g is the gravitational effect, right, and rho infinity is the outside ambient thing what we will be talking about, and that is due to the Broussines approximation, because the pressure gradient in the y direction is approximate the rho infinity g, right, which is an approximation, okay, which is known as Broussines approximation, that we will be doing. And keep in mind that this is we are not considering the buoyancy effect, therefore, this will be 0, okay. And this V x as it is 0, so this term will be 0, right, and this is the inviscid flow. So, therefore, this term will be 0, right, and then rho v, right, is basically this is rho v y is equal to 0, this is because the remaining constant. So, therefore, this also will be. So, there is no need to solve any momentum equation as such, right. Now, we will be looking at this thing, this is the species conservation equation as a, right, that is rho v x dou rho v x y f dou x plus dou rho v y y f dou y is equal to dou x rho d 1 2, that is basically fuel to oxidizer dou f x into mass generation of the fuel per unit volume, right. And similarly, for the oxidizer we can have in the similar way, and keep in mind that this is both are same. I could have put that d 1 2 is equal to d 2 1, right. It could have been basically 2 1, right, that is why I am putting that 1 2. So, this is again there is a source term for the oxidizer, and product, of course, I need not to write mass because if I solve this equation and get the mass product, you can get very easily y p is equal to 1 minus y f minus oxidizer, right. If I get this both the thing, you can get very easily. So, if you simplify this equation, what you will get, this V x is 0, right, this term will be 0 as V x is 0, right. And similarly, this also will be 0, right. So, you will get basically right these equations whichever is there. Now, how to solve this is the very important aspect one has to look at it, because we are having non-linear terms. These terms are non-linear terms, right, and this is of course the second derivative terms, right, which is has to be looked at. So, question arises how you will be solving this is a very important one. What we will be doing for that, we will be using a thin film approximation, right. That is, what is that thin film approximation? At this surface, right, what will happen? That is basically m dot at the flame surface, right, this will be all these will be occurring, that means the fuel will be getting consumed, right, because this will be mass will be fuel will be getting consumed, and then oxidizer will be getting consumed, right, is not it? Fuel and oxidizer will be reacting and then getting the product will be formed. So, at this flame surface, this all these terms will be there. But if I look at this point, this place, is it like mass of the fuel will be consumed? Will be any reaction term here? no reaction, right? Where? In this domain, this region along with the Z, nothing, no reaction will be occurring. Similarly, in this region, right, except the flame surface, there won't be any reaction. That means this term will be 0. If you look at m dot f will be 0 here, right, and f cannot get into, oxidizer cannot get into, so therefore that does not arise. Similarly, in this region, what will happen? M dot triple dash oxidizer will be 0. Are you getting? At the flame surface, this term will be there. Which one? Source term of the fuel and oxidizer will be active where? On the flame surface. Apart from the flame surface, this will be 0. On the fuel side, m dot triple dash f will be 0. On the oxidizer side, m dot triple dash oxidizer will be 0. That you should keep in mind. Are you getting? This is the thing which will be used to look at that. Okay. I will tell you that thing, so because that will be getting into that, because at the thin flame approximation, so what you will be getting is, right, if you look at that for this thin flame approximation, right, m dot f will be 0 on flame side, on fuel side. Side of flame, right, m dot triple dash oxidizer will be 0 on oxidizer side of flame. I think flame I should not, okay, let me write, alright. Basically from the flame onwards, that is the thing, that is the surface. So, if that is the 0, then what will happen? You will get a, if I look at the fuel equation, that is dou by dou y, I can write down rho v y y f is equal to d by dx rho 1 to y f by x, right, because this is 0, this is 0, right. So, I can write down that as basically if I take this out, right, inside, and rho b y is constant, right, because rho b y is constant, we have already seen from the continuity equation. So, therefore, I can take it out, I can write down that as rho b, I can say write rho b y dy f by dy is equal to rho d 1 by 2 dou y f square by dou x square, this is cancel it out, right. I am just doing that here, because as rho y is constant, already we have seen from the continuity equation. So, that means I can also write down in the similar way for the oxidizer side, right. So, similar way I can write down V y dou y o x, dou y is equal to dou d 1 to dou square y o x divided by dou x square. So, this is the another equation one can think of, like to simplify the solve, and this will be valid where? Everywhere apart from the flame surface. Are you getting? That means this is valid for what? This side, right, and this equation is valid for oxidizer side. This is for oxidizer side. This is fuel side, and these equation won't be valid on the flame surface. These both the equation won't be valid on the flame surface. Is that clear? And flame is a very thin one, like you can say it is thin, infinitely thin. Okay, that is the condition what we are doing. So, again let me repeat, that is the above two equation can only be applied to the outside of the flame surface, as both an oxidizer fuel get consumed instantly at the flame surface, right. As soon as it will come, it will be consumed, that is all, it is very thin. So, now we will have to try to solve these equations 1 and 2, which is a. So, let us look at single step irreversible reaction, that is fuel 1 mole of fuel is reacting with, or 1 new moles of oxidizer going to the product of nu plus 1 mole of product. So, if you look at this reaction as m dot triple dat double mass flux of fuel, right, is equal to oxidizer by nu is equal to minus product by nu plus 1, because you see I have taken minus this side, that is all. And from this we can basically look at this m dot flux is equal to what? This is equal to this m dot f, if you look at, is equal to rho d12 dyf by dx. If you look at, this is my flame, right, flame F, you are coming from this side, minus flame, right, F you can say. And similarly, I can do for the oxidizer as well, right. Okay. And similarly, I can write down of oxidizer is by nu is nothing but rho d by nu oxidizer by dx, of course positive side, this is, I can say, negative side here. I mean, like, basically flame surface, this is flame F and it is coming from negative side, and this is the positive side I am saying. So, if you look at, this is basically this dyf by dx f is equal to nothing but 1 by nu dy by dx at f. So, from this I can say very easily that yf is equal to yf is equal to minus y oxidizer nu, and which is nothing but your yr, and this is your universal variable, right. One of them, if I will get that, that means all these equation 1 and 2, right, I can keep in mind that the rate of fuel transport from center to the flame surface is equal to a stoichiometric rate of this proportion, right, that is the meaning what is saying. And yf be the mass fraction of the reactant. Instead of solving two equation of fuel oxide, we can solve a single equation, and that is basically I can say Vy dou yr divided by dou y is equal to d12 dou square yr by dou x square. So, I can put that thing and then do that. This is my equation we need to solve, right, and this is the universal variable, that is yr. This is your universal variable, right. So, instead of solving 2, I am solving the one equation. So, let us say this is your equation number 3. So, in the next lecture we will be basically looking at how to solve this equation and get a some kind of a flame surface and other thing. Okay, thank you very much.